Okay, perfect. So today we're going to continue and hopefully conclude our discussion of the connection between these collider physics observables and correlation functions. And so last time, what we were working on, before I started going over time, was the relation between 3-point functions of local operators and 1-point functions of fluxes in colliders. And so we said that the nice thing about 3-point functions of local operators is that their structure is largely fixed depending on their dimensions and their spin structure. And so we started off with this very simple example of trying to measure the 1-point function of this energy flux operator in some scalar state. So this is where we were last time. So we had something like this, where this is a scalar operator. And so physically what one is doing is one is pinging your system with some scalar operator so that it's symmetric under the rotation group, and then you're measuring the energy flux coming off at some particular angle theta on your sphere. And so we said that this has a very simple expression, which was not very impressive, namely that because this is a scalar operator, this object is rotationally invariant, and so it's uniform over the entire celestial sphere. And then we were able to fix this constant just using energy conservation. So from doing this, one doesn't learn very much other than just how to kind of phrase questions in this language. So then we just started, before the end, talking about a slightly more interesting example of having a spin 1 source. So what we wanted to do is to upgrade this from scalar to a spin 1 or conserved current that produces our excitation, and then we measure the 1-point function of energy at infinity. And so the nice way of doing this for kind of toy calculations, which are actually very useful to try going through, and so I highly recommend it, is just to couple either a scalar or a fermion to some U1. And so if you do this, you get 2 currents, which will be useful, or which we'll be able to use in kind of toy calculation. So one for fermions, which is just the standard one like this. And then one for scalars, which is also good. So it's an easy exercise to work out just using Noether's theorem. That in this case, the conserved charge, or the conserved current, sorry, is the following. And so these will be nice concrete examples which one can use in perturbative calculations. And so now what we want to do is to consider 1-point functions just like this of these specific operators. So we want to insert these operators, which now carry some polarization vector, which can be dotted into this direction n, where we measure the energy flux, like this. Okay, and so I said last time, so I just wrote down the expression, which I'll do again, and then we'll actually get to derive some of the consequences from this. So I said last time a good exercise to do was to write down the most general form of this 1-point function. So one can measure now the 1-point function in these states with some, so this is bad notation, but this is a polarization vector. So this is, not to be confused, this is polarization vector, which you dot into these currents. And this is the actual energy flow operator. Unfortunately, they have the same symbol, except one is supposed to be big and one is small, but that's hard to see on the board. And so what we wanted to say is what is the most general form of this. And so this was an exercise that one was supposed to do. And so in this state, specified by this polarization vector, you can use both the fact that it's a spin 1 current, that it's quadratic in this polarization vector, and that you have conservation of energy to show that the most general form you can write down has only one unknown parameter. And I'll write this in 2 ways, just as kind of a hint for how to derive this. So you can choose to write this in this particular way. And so you have one unknown coefficient, which will be of interest to us. So in the scalar case, it was just completely fixed. Whereas in this case, we have one unknown coefficient. And this can be written in a slightly more intuitive way in terms of the actual angles on the sphere. So in particular, in terms of the angle between this polarization vector and this, where you're measuring the energy flux. And so this is the expression I wrote last time, although it was scrunched. So now I'll write it bigger. And so again, the interesting thing is that this is fixed by symmetry, or by energy conservation. But this coefficient here depends on the dynamics of your theory. So if I change the interactions of my theory, I'll get different results for this coefficient here. And again, the reason why one writes it as this cosquared theta minus a third is just so that this term integrates to 0, and so you just get out the total charge. And so I should just say, for those that want to, again, extend a little bit this exercise, the analogous statement in terms of the local, or the 3-point function of local operators is that if you consider the 3-point function of 2 currents and a stress tensor, that there are 2 conformally invariant tensor structures. And then you have one constraint from energy conservation, or from the Ward energy. But at the end of the day, one gets to this nice formula for how energy is distributed on the celestial sphere. And so this may not look that impressive, but it's actually a very interesting formula. And so one thing which one can do, which is essentially trivial from the collider physics perspective, is one can enforce that this object is always positive. And so there's a more general theorem, which is that in any state, the expectation value of this Anik operator, or this energy flow operator, is greater than or equal to 0. And so this can be proven independently by other means, but for here, or here we'll just take it as an example, or as a, we'll assume it's proven. But you should also see that it's kind of essentially trivial why this holds, at least in perturbation theory, at least from the collider physics perspective, because when you're computing this, if you think how you're computing this object in terms of Feynman diagrams, what you're doing is you're doing some integral over phase space of a matrix element squared, which is manifestly positive, with some constraint on there being some energy or some particle going in some particular direction n hat. And so the nice thing, or the reason why this allows you to say interesting things, is you have one representation where this thing is manifestly positive as the square of an amplitude, and then you have another where it's a correlation function which is not manifestly positive. And so it allows you to actually prove quite interesting things about generic field theories. And so in particular, you can just demand that this expression up here is positive. And what you find is that this actually places a constraint on the value of A3, or A2, in the way I wrote it. So in particular, what you get are what are called the conformal collider bounds, or an example of the conformal collider bounds. which place a sharp constraint on the value of A2. So in particular, one has that 3 and so it says that in any theory that you have, regardless of the dynamics, you have to get this particular value of this A2 coefficient. And so this is similar in spirit to what people do, for example, in the conformal bootstrap. But here you can really phrase it in terms of kind of collider physics thought experiments. And so this is why this is interesting, or these kind of observables are interesting from a purely formal perspective, is they allow you to probe or kind of prove results about the underlying dynamics of the theory. And so these you can think of more generally as kind of collider physics thought experiments. And so it's actually now possible to prove this using other techniques, but it's extremely non-trivial. And so by kind of thinking about these collider physics thought experiments, you can prove a certain class of questions or derived constraints that are very different to those you get from other observables. And so it's kind of an interesting way of thinking about things. And so the other thing which one can do is often when one derives bounds, you want to know what theory it is which kind of saturates these bounds. So what theory, sorry, this should be. So you would like to know what theory it is that saturates or gives the most extremal values of these bounds. And so this is also an exercise you should do. So, and it's actually a surprisingly simple exercise, is to compute. So what you should do is to compute the value of A2 in both a free scalar or for and for a free fermion using these two currents which we derived over here. Or we didn't derive, but that I wrote down over here. And so this is all you do to do this is you really, since it's a free theory, when you insert this operator, if you do it using Feynman diagrams, you really just have either a free scalar going one direction and the other direction. So this can be either your free scalar or your free fermion. And you just compute the Feynman rule for this. You dot it into that particular polarization vector that you choose. And you literally just take the mod squared of this and look at how it depends on the angle between the direction that the particle is going. So in this case, it's the only particle that can go into the detector and the polarization vector here. And so it's a very simple calculation of just kind of squaring this tree level matrix element. But you'll find, it's actually very interesting, that you'll find that these two theories saturate these bounds. So they're kind of the extremal things. And so in particular, one will find that the free scalar saturates this bound up here. And then the free fermion saturates this bound down here.
Why is it exactly negative half of scalar?
Why is it exactly negative a half of the scalar? So that's a good, so I'll show in a second. So one way one can understand these, so I don't have a direct intuitive answer from the Feynman diagram picture, but one way one can understand this, and I'll mention this in a second, is that this value of A2 will be exactly 0 in a supersymmetric theory, because you can relate this spin 1 operator to a scalar operator. And so in that case, what happens is a cancellation between the fermionic degrees of freedom and the bosonic degrees of freedom. And so that's something that has to happen. Why it's just, from the Feynman diagram perspective, negative or a half of it, I don't have a good answer. So typically you have, the negative is because you have kind of like fermionic statistics as opposed to bosonic. Why it's exactly a half, I don't know, apart from, like, one can show it afterwards. But I don't have an inherent intuition for why it's negative a half, yeah. Yeah.
So this is true for propagators, for scatter field of from without mass because we need conformal variance.
Yeah, yeah.
So, but if they are interacting, don't we risk to introduce a scale?
That's a very good, so that is an excellent question. And so here I will assume that one can turn on those interactions in a way so as to keep conformal invariance. And so that's a big assumption. And so that's why these are called conformal collider bounds. And so there are some, so in let's say like in QCD in perturbation theory, which I'll show in a second, these will still hold because you do not see the presence of the scale in perturbation theory. But if you actually introduce a scale, then you need to be a little bit more careful with what you're doing. And in particular, for example, if you have massive particles, they no longer just go to null infinity. You have to be a little bit more careful. And so this is something, for example, like Evan has worked a lot on, and so you can ask him about this. But in this case, one is really assuming that all the particles are massless. Otherwise, like what this, so the fact that this thing is positive will still remain true, but how to interpret it as easily in terms of specific kind of objects in the theory, that's where it becomes a little bit trickier. And so this is where one starts to use, and I'll use it a little bit. So this one, because it's free, you really just have to, you need it massless. And then when you turn on the interactions, just that you don't see the scale. But then I'll use in a second a stronger, to actually fix this in terms of other properties of the theory, I'll use a stronger like superconformal invariance, which is definitely not true in general. And so this is a completely general statement. If I have massless things, then I'll slowly strengthen it and use more and more properties. Yeah. Any other questions? Yes.
So just for free scalar free fermion,
Yeah.
do you get something weird if you have free spin one particle with a photon?
So you need, so this is, the reason why I don't, so you can do this in general, no. So this is a specific thing where I've coupled it to a like spin one current. And so you need to put in some different, so in that case, what you can do, so there's other conformal collider bounds, which you can derive for, so you can do this in any state. And so here I've done it for coupling to like a spin one. But in that case, what you want to do is couple to like, or what you want to study, because there you don't get like a spin one conserved current that you couple to, but you can derive an analogous, so you can couple to like the stress tensor. And so you can imagine this is kind of like the Higgs to two like gluons or something, loosely, or you could couple to that if you want. And so you can study, for example, this OPE. And so there, because it's like a photon, you want to study in like a spin two initial state. And so this object, when you turn it into a detector, will also be greater than or equal to 0. And this just has a more complicated angular dependence, which is why I avoided it. So it's actually done, if you want to read about this is done in the original Maldacena-Hoffman paper. But then instead of having just one, because it's now kind of spin two, instead of just having one unknown, you have two, and you can derive bounds on those. So it's a very interesting thing to do, and you should definitely try doing it. And so more generally, you can put any state here and derive some bounds. And so it's a fun thing to do. OK, good. And so it's worth just trying this to see how simple it is, and that you actually, from doing a kind of tree-level calculation of free theory, can kind of derive very nicely these bounds. OK.
So was that for a real scalar?
Oh, so this is for a complex. So I want here to couple it to a U1, and so it's for a complex scalar. So this is also for, with this is for, I've done it with a Dirac. But so this depends a little bit, and this is kind of whether or not you have like factors of 2 here. But I've just done it in this simple way so I can couple it nicely to like the U1 in the standard way. But you can rephrase this in terms of any other degrees of freedom that you want. Yeah, that's a very good question. Yeah. OK. So yeah, so we've been able to derive these nice bounds from this. And then what I got to at the end of last class is you can kind of check, or a sanity check, is you can compute this to higher orders in perturbative QCD. So this is where your question about not generating a scale is important. And so if you compute this object in perturbative QCD, So at the lowest order, you just have free fermions, just like this. But then if you emit a single gluon, which can now also, for example, go into your detector, like this, what you now find is that this A2 in QCD is minus 3/2. So this is the kind of extremal version, or extremal value. And then you get a positive correction over here. And so you can see that it is staying within the region. So if you're allowed between minus 3/2 and 3, it's kind of staying within this bound. So it's a healthy theory, which is obvious, or we should have expected that QCD would satisfy this. Okay. So now what I want to do is just to mention, so this is kind of more a statement of certain facts, because I don't have all the time to go into the background of it, but I just want to show how this can be used a little bit more powerfully when you have more symmetries which actually fix the structure of the value of this A2. So in certain theories, so there's two ways in which this is useful. So one is if you actually know fully this 3-point function. So this is nice, you can compute it in perturbation theory, but that's just what we did anyways before. And so if you have access to this 3-point function, you can use it to calculate the distribution of energy flux non-perturbatively. And the second is if you know, so this is kind of maybe a bit obscure. If you didn't know what this A2 is, you place some bound on what it is, but it may not be the most interesting quantity. So in certain theories, you can express the value of A2 in terms of other parameters of your theory. And I'll give an example in a second. Of your theory and use this to bound them. And so this kind of shows why studying these correlation functions in energy flux are kind of useful just from a purely theoretical perspective. And so I just want to give one example for this, and then we'll move on to higher point functions. And so this is just what I want to do is just give an example, so I won't be able to, yeah.
I'm still getting confused about what the argument for alpha is. There is like for a CFT, I know what the coupling is. With QCD, I can just tune it to any scale and I can violate the bound as much as I want.
Yeah, so this is where, yeah, it's a bit problematic. So in a non-CFT, yeah.
You repeat the question.
Sorry, yeah, so the question is, if I'm not in a CFT, what do I really mean by this, which is a very good question. And so you should think of it, well, at some point it just breaks down. So you need to be in a regime where it's kind of perturbative and under control. And so you're saying that these alpha S corrections are small. So first of all, if this becomes at all comparable to this, because this is an order 1 number, then you've well broken down your perturbation theory anyways. And so all it's saying is that the leading coefficient for this will always be positive, and that's true independent of scale. And so of course you can, yeah, so this will always be positive actually, and so it's always fine. So you have to be a little careful in general about some of these things once you have running scales, but they typically work, right? And so as long as you say that alpha S is positive, this is good. And that once it becomes kind of order 1 or anything, so you could say like, why can't I just violate the bound on the other end by making it arbitrarily large? But there you've just completely lost control of perturbation theory, and non-perturbatively, it would still be within this bound. But then you just have all the other terms in the series are equally important, and you just completely lost control.
You could technically use that to bound the growth of the perturbative coefficients for a bit.
Yeah, in reality, no, probably. But in principle, yes. So and so in real world QCD, once the coupling becomes large, you just you lose control of expressing it in terms of this language. But it kind of bounds perturbative coefficients, is how one should view of it. And that's the nice reason in the example, which I'll show, is that one can actually obtain like A2 non-perturbatively, and it places a non-perturbative bound on the objects. But yeah, that's a very good question. So just an example of why this can be useful. And so unfortunately, I don't have time to quite go through the background, but I just want to state a result which allows one to express this A2 in terms of certain other coefficients. So it is a fact so that in n equals 1 supersymmetric conformal field theories, so this just allows you to have a little bit more control. You can write an exact expression for this A2 in terms of two parameters. So you can write this for a certain set of currents. Where physically what these C and A are certain anomaly coefficients. So, and this is in a D equals 4. So in D equals 4, when you couple your field theory to some, or when you put it on some curved manifold, in general, the trace of the stress tensor can have two anomalies. So one is proportional to the Wild tensor. And so again, this is just a kind of statement for now of why this can be interesting. And one is proportional to the Euler density. So I won't write out the explicit expressions for these, but they can just be computed in terms of like their Riemann tensor and stuff. So this is Weil, and this is the Euler density. And so these are objects which you typically understand in your theory. And they may be things which you don't normally think of when you think of collider physics experiments. So they're much more kind of abstract things. But the very nice thing is because these constrain the structure of this JJT OP of local operators, they also appear as the coefficient here. And so you get this relation for putting this object on a curved manifold, which is due to the fact that it's the stress tensor, to what you'd actually measure in the energy flux at a collider. And so it's kind of an interesting relation that you get by working in this language. And so this is an exact formula, and it also implies, in particular, using these bounds, and so this is a very non-trivial constraint on the properties of these anomaly coefficients, which one has derived by doing this kind of nice, simple thought experiment. And so it's kind of a neat way, in my opinion, of how one can use kind of collider physics observables to constrain properties of your field theory. And so this is very hard to prove by other techniques. And alternatively, you can now, in this theory, though it's relatively simple, you have the exact result for the energy flux that you'd have in this kind of toy collider in your n equals 1 supersymmetric world. And so this is kind of nice. So we've answered one question in collider physics, this distribution of energy in a particular class of theories, and we kind of rephrased it. And so now what we want to do is to move towards slightly more complicated questions. But I just want to give two exercises or things one should think about using these 3-point functions. There's a lot more one can do. So 2 entertaining exercises. Again, it depends on your definition of entertainment, but so one thing is related to your question about why you have this minus 3/2. So because you get a positive coefficient for scalars and a negative coefficient for fermions, you could ask, can I put some combination of them where naively I would have some angular distribution, but it exactly cancels. And so in perturbation theory, this would be kind of a miracle. But if you do this, you can use properties of the source. So you can try taking combinations of fermions and bosons to get a symmetric distribution. And then you can try and understand why this actually happened or why you were able to cancel it. And the kind of hint is that for the particular combination you will find, this spin 1 current is actually related. So you have a relation. In this case, you'll have some supersymmetric relation between the spin 1 current, and it will be in a multiplet with a scalar current. And so this is the case that we worked out before, which was spherically symmetric. And so in these cases, even though you naively or individual components in perturbation theory have angular dependence, you can relate it to a scalar, and so you know that everything's going to cancel out. And so this is actually very nice and simplifies things in a lot of cases. And then the second one, which is fun to try, is so in this case, we considered these currents under some U1 symmetry, but you can also do this under an anomalous U1 symmetry. And instead of measuring the energy flux at infinity, you can, just because you know you have a cubic anomaly, you can measure the 3-point function where you have a state sourced by your j. You then measure the charge associated with this j at infinity, like this, as a function of the angle theta. And you'll find a very interesting result, namely that you have a kind of forward-backwards asymmetry. So it's now asymmetric. And so this is something that one often gets in certain collider experiments. And so you can understand it in this very nice way of a specific anomaly. And so these are kind of fun things which one can play with and kind of get different distributions in energy from these 3-point functions. OK, but that's for you to do in your own time. And so are there any more questions about these 3-point functions before we move on to actual kind of dynamical things which come from 4-point functions? Yeah.
Just in that expectation value, there is always a q over 4 pi as an overall factor.
Yes, absolutely. Yeah, good, good, good. Yeah. So I've normalized like q over 4 pi to 1. Yeah, exactly. Yeah. So. Very good. Yeah. Any other questions for this section? OK. So now what I want to do is to move on to actual dynamical questions. So when I showed you these plots last time, they were all measurements of multiple correlation functions, because that's what you really want to do if you want to study, for example, the internal structure of jets. And so to do that, we have to go beyond these 3-point functions that we've been studying and start looking at 4-point functions. So in particular, let's say what we want to do, and this is as far as we'll get, is to measure correlations between 2 detectors placed on the sphere. So this can be at some angle θ1. And so this is, for example, what is actually measured at the LHC in these plots which I showed you. So the way that one can compute this is now in terms of 4-point functions of local operators. And so now the problem is that these are much more complicated objects. And so in particular, they're no longer fully fixed by the symmetry structure of your theory. And so before I wrote down expressions for example, for the 3-point function of scalar operators and show that it was just fixed up to a single coefficient. So now we can try doing the same thing for 4, even before going to stress tensors, 4 scalar operators. Find a kind of problem, or of course something which we expected, that we wouldn't just be able to get this for free, is that this is no longer completely fixed by symmetries. And so in particular, one can show, so you can use different conformal transformations to show that the most general form of this, so before we had just some number, but now you have a generic function of 2 variables up here. And so these variables are things that appear in many different scenarios, and they're called conformal cross ratios. And so in particular, what one can write down, their expressions. And V is very similar. And so one way of understanding why you can do this once you have 4 points is that you'll see, so we want things that are invariant under scaling. And so if I've written these correctly, you'll see that each of these variables appears the same number of times in the top and bottom of these expressions. And so I can rescale these and it has no effect. And so what I get is actually a generic functional dependence on these U and V. And so this is a much more complicated object, and it's no longer just fixed by symmetries. And so now, if we want to actually understand this in collider experiments, we need to have some limits or theories where we can exactly, or where we can compute this dependence. But we can't just fix it in terms of the properties of the theory. And so, unfortunately, there's not very many cases where you can actually understand this in full generality.
Say anything even about the class of function or the genus or...
You can definitely say things about it, but it's not completely fixed. And so, for example, what the conformal bootstrap is trying to do is constrain those classes of functions. And so generic should, or generic is not really the right word, but it's a non-trivial function of these variables. And it's in general, so like in perturbation theory, it has certain structures, or in different theories, it has certain structures. But it's a non-trivial, maybe that's a better, non-trivial. It is highly constrained, but it's a non-trivial function of these 2 conformal cross
So
ratios.
the complexity in perturbation theory just grows with the order.
Exactly. And so in perturbation theory, it'll typically be polylogs and their generalizations. Yeah. So where can we understand this observable? So examples where we can actually understand this. Which are much less impressive than we could do for the 3-point function, are so one, we can understand this in free theories. Sorry?
1 plus U plus
Yeah, so yes. We can understand this in perturbation theory, which I'll show in a second. So this is very useful, for example, in QCD. We can understand this at strong coupling using ADS-CFT in certain theories. In certain cases, we can get this from the conformal bootstrap. And in other cases, which I'll mainly focus on here, we can understand it in specific kinematic limits. And so this will often be good enough for many cases that we want, for example, at the LHC. And so the two examples that I'll have time to discuss a little bit are perturbative theories, where we can just compute this object in perturbation theory. And then what I'll try and discuss is how one can use this to kind of reorganize our thinking about certain kinematic limits in QCD. But I should say that more generally, this should motivate your interest in this kind of study of these 4-point functions, for example, in conformal field theories, because if you have them, you can then use them to compute non-trivial kind of collider physics observables using them. And so as people are starting to be able to compute them, one will actually be able to get kind of interesting physics out, or interesting for a collider physicist. Okay, so now what I want to do is just study a little bit the structure of these 2-point correlation functions of energy flux in perturbation theory, to just kind of give some intuition as to how one can get these plots, which I showed last time. And this will also give us an understanding of which limits we want to study. Okay, so perturbation theory, or behavior in different theories. So what we're going to try and study is, again, this 2-point correlation function. And I'll do it as a function of a variable which I'll call z, which is just related to the angle between the two detectors. And so in particular, this z ranges between 0 when the detectors are on top of each other, and 1 when they're exactly back to back. And so now what we want to just understand is what this looks like in different theories. So we can measure this 2-point function of the energy flux as a function of this variable z. And so the first thing we can do is to compute this in just a free theory. And so this is extremely simple, because what happens in a free theory, so actually, does anyone know what this distribution looks like in a free theory? So in a free theory, as I drew earlier, I just have two particles which come out exactly back to back. And so in general, when you're computing these in perturbation theory, right, what you want to do is you integrate over the Lorentz invariant phase space of your matrix element squared. You weight by the energies of the pairs of the particles, and then you have some delta function minus the angle between them. So if I do this in a free theory, what will I get? Good. Yeah. So what are your fingers gesturing to? Yeah. So there's two configurations. So one, I can put the two detectors. So it will come out back to back. And so I can put the two, it will come like this. And I'll have an angle of pi between my two detectors. And the other way I can do it is I can put the two detectors on the same particle. Or kind of, they're both right on top of each other and the particle goes through them. And so in this case, in the free theory case, what you get are two delta functions. Sure. So here it's a free theory in 3 plus 1D, but I'm only measuring, so then I have a two kind of sphere where these things are going out to, and I'm only measuring the angle between them, so like the dot product. So what I'm measuring is the dot product between the two vectors. So this, yeah. Sorry.
I mean, if the 3 plus 1 is a 3,
Yeah.
then should I think the S matrix is identical?
Good. So good, excellent. So this is not the S matrix here. This is the matrix element for when I insert one of these sources. So I insert, let's say, this phi squared or this j mu that I put before. So I insert 2 operators, and then, or I insert one of these operators, and then I see what is produced from it. So you're like forcing, so instead of sending them in from infinity and they just do nothing, you're kind of putting 2 at the origin and they just propagate out.
Can I understand this as being theory, the 4-point factorization?
Yeah. Or you can also compute this just with Wick contractions. Exactly. Yeah, absolutely. Yes. Very good question. And so what you get in this case is 2 delta functions, 1 at either end. And so in the free theory, this 2-point function is just, you can normalize it in some way, a delta function plus a delta function at 1 minus z. And so this is not what you observe, for example, in real-world QCD, like I showed you last time. So the other example, which you can do to gain some intuition, is if I have a very strongly coupled theory, or in particular an infinitely strongly coupled theory. And so instead of producing 2 particles, if I just produce some like homogeneous ball of fluid, which comes out. And so in this case, can anyone guess what the structure of this correlator is? Flat. Yes, very good. So the other case for intuition, which is good to have, is, so this is free. This is strong coupling. Like this. So the 2-point at strong coupling is like a half or 1. And so then, can one guess, or we showed last time, or I showed this plot, of what it looks like in QCD. So in QCD, it looks like some kind of combination of the 2, like this. And so it's very hard to find any, because we don't know the exact value of these 4-point correlation functions. It's very hard, and so this, if I add a thing, or let's say a weakly coupled theory. It's very hard to find kind of exact functions which interpolate between these 2. And so the best we can kind of do is to compute this in weakly coupled theories and perturbation theory. And then we kind of see by I it's kind of in the middle, but this is, not fully satisfactory. So what we really like is to be able to do this exactly for all values of the coupling. But instead, what we do is compute in perturbation theory. And so this is where you'll see your question about what types of functions appear. You'll see that it has some nice logs and stuff that will appear. Okay, so perturbation theory. So what one can do is to compute this at the first non-trivial order in perturbation theory in, for example, QCD or your favorite other theory. And so in that case, what you want to do is to use this expression exactly as shown here, but as related to your question. So now the 2 particles don't just propagate off freely to infinity. You can add a single non-trivial interaction, so a single emission, for example, of a gluon. And so a very good exercise to do is to take this matrix element for, like, let's say e plus e minus to 3 partons, square it, and try and do this integral over the phase space. So this is something that's not hard to do, and it actually ends up giving quite nice answers. So you can do this in your favorite theory, and I'll just write down 2 examples to highlight certain universality between them. So if you do this in n equals 4 super Yang-Mills, which is just some kind of slightly simplified version of QCD, what you find is it's just some rational function of z multiplying a logarithm like this. And then if you do it in QCD, which I recommend trying, you'll see why people like n equals 4. And so it has a slightly more, or maybe I'll move this up. And so the exact form of this won't matter. It's mainly for illustration purposes. So it's a good exercise to try and get either of these results. And so if you plot what this looks like in this plot shown up here, or I'll just replot it, it just behaves like this. So it's just kind of a boring function which just goes like this. And so these aren't particularly intuitive. And so they also contain a lot of kind of uninteresting information. And so this is related to the fact that this object here is not kind of fixed by symmetry or is some very complicated object. And so to try and gain some intuition about what's actually going on or what are the kind of interesting questions to study, we can expand this in different limits to try and look for kind of universal behavior. Yeah. Good. So this is the leading order term in the alpha S expansion. Yeah. So I've removed all normalization in both cases, and so this is the first order term. So it has higher order correction. So this is actually being computed. So this is like alpha S over 4 pi times this. And then it's actually, if you want to watch a nice YouTube video, there's a video of Lance Dixon writing the expression for this, which takes up like 10 chalkboards. But it can be computed exactly, and if you want to watch him write it out, that exists on YouTube. Yeah.
Axial coupling, will this become asymmetric?
Yeah, so this is for, here I've also spin averaged even. So I've done it even simpler. So yes, in general, this will depend on the, once it's not a scalar operator, it will depend on the, so it can be asymmetric, and it will also in general depend on the just polarization vector to the normal piece. And so here in the QCD case, I'm still using this psi bar gamma mu psi, but I've spin averaged it over the original polarizations just to make it a little bit simpler for illustration. But yes. Yes.
Does this QCD calculation account for a confinement? Because we said it.
No.
Okay.
Yeah, definitely not. And we'll get to that in a second. And so one of the reasons why you see that there's even many problems before confinement is this just diverges, as we'll see in a second, in both endpoints. So this is just a leading order. It just has this, where the quarks and gluons are massless. So now what we can do, so this is a kind of complicated mess, particularly in the QCD case. And so what we want to do is to look for some simplifying behavior where we can try and understand its structure better. So as I said, for these 4-point functions, in general, you can't understand the full thing. And so instead, what you want to look for are simplifying limits. So the two limits which we can take, which we fortunately discussed a little bit last time, or we can take what is referred to as a collinear limit. Where we take the value of z to 0. And you can just take these expressions and expand them in Mathematica. And you'll find that in n equals 4, it just behaves like 1 over z. And in QCD, it has the exact same power law behavior. It's just that it now has a slightly different coefficient appearing here. So the other limit which we can take, which are just the kind of two limits in this plot, is the back-to-back. Which corresponds to z going to 1. So you can again expand this. You just take this function and expand it in Mathematica. And you find again that it has a very simple behavior. And in particular, you actually get the exact same thing in QCD and in n equals 4. So not only are the functions the same, but the actual coefficients are the same. And in QCD, or this is exactly the same in both QCD and n equals 4. And so this is a very simple answer in both cases. So it's just some kind of power law scaling. And in particular, it has some form of universality between the different theories. So in particular, the fact that it's identical between these two theories suggests that there's some kind of universal dynamics which are governing it. And so also in general, when you have a simple power law, you would like it to be dominated by kind of one single operator that you can understand and try and understand. So these are leading order in the coupling, but we would like to be able to understand to all orders in the coupling, for example, the leading behavior in either of these two limits. And so I'd originally wanted to go through in detail both, which will definitely not be possible. And so instead, what I just want to do is to give the result for how this behaves to all orders in the two limits, and then describe how one can understand the collinear limit using both factorization or effective field theory techniques and conformal field theory techniques.
So is this then true of every order that the back-to-back limit, the highest resonance algebra is the same?
Yes, yes. Yeah, exactly. And so the reason... So, it's conjecturally and it's been verified. So I'll write down an expression in a second where one can see why it's true. So in particular, or I'll write down the expression and then I'll comment on why you can understand that it's true. But it's been checked to we checked to like 3 loops or something and it holds. But yeah, so all these things are typically conjectural, but one definitely believes the conjecture. Okay, so unfortunately, we'll not be able to go through the full derivation of these, but I just want to show that you can get a very universal formula which describes the behavior in these endpoints to all orders in the coupling. And so in particular, the claim, and so one of these will verify. So in the z to 0 limit, so in this first one, the only thing that is modified, or that the exact expression to all orders in the coupling, is that this has some coefficient which is proportional to the coupling, but is independent of the variable z. And then it has a scaling which goes like this, where this coefficient, this is a function just of alpha s, or just of the coupling of the theory, and this is theory dependent. And so later on, what we'll try and do is explain what actually is this specific anomalous dimension. And then in the other limit, as z goes to 1, and this one we unfortunately will not have time to explain, is that it then again depends on a particular, or again just a constant, which I'll call h2, and it has a slightly more complicated formula. But I'll write it just to show that there's something very concrete. And then this is getting a little squished. It doesn't matter if you can't read it. Because the only thing that's important, so is that this is just some formula. And the thing which is nice about these formulas is that these only depend, so if you're interested in like the scaling behavior and not the normalization, this depends on a single number, which we'll try and understand what that number means, but as opposed to this whole function up here. And in this one, it depends on 2 numbers, this and this. And so this is where the dependence on the particular theory enters. And so the nice thing about this is that these are true, or this is true completely generically in any conformal or near conformal theory, and this is true in any conformal gauge theory. And so what you've done is you've reduced, by considering these scaling limits, you've reduced the problem to studying a certain set of numbers. And so related to your question, it is known, or at least much more strongly conjectured, that this and this are universal transcendental weight. And so then, for example, at leading this in my normalization, the cusp is just 1, and so that's why they're exactly the same between the two. And so the nice thing about this is by considering this limit, as I just said, you just need to understand these numbers. And so since I only have 10 or so 15 minutes left, my goal will just be to try and understand what this number is, and in particular, how we can use 2 different approaches to study it to kind of resolve certain issues in the QCD literature about what this number actually means. Are there any questions before we go on? Yeah.
The gamma call, is it dependent on alpha as well?
It's also dependent on alpha. It's just smaller.
B naught, is it their parameter? Or is
No, B naught is just some. B naught is like it's just a constant in terms of the Euler gamma. It's just some normalization, which makes it. It's just like a known number. Yeah, sorry. But the pieces that actually depend on the theory are these 3. And so we would like to understand those. Yes. Hopefully that's better. Okay. Now hopefully we can understand what this number is. So what we'll try and do in the last 15 minutes, and then I'm happy to answer or explain more afterwards, is understand how one can use both effective field theory techniques and conformal field theory techniques to understand this particular number up there. And so the first thing which I wanted to emphasize a little bit is why this is a slightly different problem than what you typically consider using standard effective field theory techniques. So the 2 ways that we'll try and analyze this are using effective field theories and using an operator product expansion. And then by doing it in these 2 ways, we'll be able to derive some interesting properties of this number. So first, the way that one is typically taught effective field theory, so standard effective field theory, which is why these problems are a little bit harder, is you think of often, for example, having some massive particle. So you have some scattering process, and you have, for example, some Z or something which is in between. And this is a very heavy particle. And so in particular, because the propagator has this structure like this, if you're at momentum, which are much smaller as compared to the mass of the particle, you can expand this over a set of local operators. So I'll just write this as like this. And so you can just have an expansion in terms of local operators in your theory. And so this is really because this is a kind of Euclidean actual short distance singularity of your theory. So what's happening when you do this is you're really bringing these 2 together, and you're expanding in a set of local operators. And so this is why this style of effective field theory is very well understood. So we know how to write down local operators, and so we can do, for example, the standard model effective field theory, and we understand it very well. Alternatively, the kind of analog of this in the conformal field theory language is what is, or just in the general field theory language, is what is referred to as the operator product expansion. Which is just another way of saying this, namely that if I have 2 operators, and I bring them very close together as compared to some other operator that I have out here, I can just expand them over some set of local operators. And so this is really just doing the exact same thing as one was doing up here. So in particular, I can write some very schematically some product of local operators as some sum over operators at a specific location. And so one can ask, why can't I just use kind of these standard effective field theory techniques to analyze the behavior in these particular limits? So this is, again, an expansion of the field theory. Just like here, I'm expanding a small momentum. And so why can't I do this in this case? And so the reason is that these are really kind of Euclidean singularities where you're really bringing these two points physically close together in space. But if you're working in Lorentzian signature, you can have a much richer class of singularities. In particular, because as you take x squared, or the distance between the two operators, to 0, you don't have to actually necessarily bring the operators close together. So in Lorentzian signature, I can have some kind of light cone direction like this, and I can put two of my operators on the light cone. And so they can be very far apart, but they can have the actual x squared distance between them going to 0, even though they're smeared along some light cone. And so in this case, this leads to a much more complicated set of singularities. And in particular, these generically involve non-local operators. Of which these energy flow operators or Annick operators are a specific example. And so one can wonder, or why I still have the intuition that you should have some universal dynamics in these specific limits. And if we focus on this collinear limit, so in this collinear limit, while you expect to have universal dynamics, the reason is that what's actually happening is you have some scattering which produces your particles. And so I have some complicated many loops here. And then if I have my two detectors off here, so at one angle here, at one angle here, what produces the strongest singularity, in particular this 1 over z singularity, is where I have a nearly on-shell particle which propagates a very long distance before going into my detectors. So this is this z. And so in this case, the way that one should think of it is no longer that these two things are happening at a very short distance, but rather that they're essentially infinitely far separated. So it doesn't matter at all what's happening in this very complicated process here. So in particular, it doesn't matter at all on the behavior of the source. What you do is you have just some states of your theory, so essentially single particle states. Of your theory, which propagate off to infinity. And so instead, you just need to know how to produce these single particle states, and then what the correlator looks like on these single particle states. And so what I want to do is to show how one can make this precise using a kind of factorization theorem, and then derive a property of this gamma 3. And so hopefully I can have maybe a few extra minutes. So how can we guess the structure of this factorization theorem? So unfortunately, we won't be able to derive it, but we can guess it. So let's say we try and write down an expression for this cross-section as a function of the angle, which describes only the leading dynamics in this small angle limit. So the way we want to think of it is kind of take this picture literally up here, where we can imagine something that produces single particle states with some momentum fraction, which I'll call x. And then it's these states which then kind of propagate for an infinite amount of time and then decay into these two detectors. And so I really want to think of kind of inserting a complete set of states in there and then taking only the single particle states, which will give the leading behavior. And so the way we can do this is we can write this. It actually has a very simple form if one doesn't define the operators that contribute. So what I want to do is have some hard function, or what I'll call a hard function, which produces some particles, so for example, a quark or a gluon, with some momentum fraction x. So here this x will be the energy of this intermediate particle normalized to the total energy. And so I can produce these at any different energy, and eventually they go into my detector. Then what I have is what is referred to as a jet function. And so notice that this one is completely independent of the specific measurement I made. So this is just some universal property, or this is some property of the theory, whereas the measurement will appear in this. So this will depend on this variable z. Like this. And there's a factor of x squared because I have two of these energy weights up there. And in particular, what's appearing here, this is just the invariant mass scale of the intermediate propagator. So now what one can do, so this, the way one should think about this is it's giving a kind of splitting between where I separate the physics of these two specific properties, or of these two processes. So this is what is defining this mu. And so I can derive some renormalization group evolution equations which essentially move this back and forth. And so the evolution equation for this is actually exactly what was given in Stefan's lecture. And so this is this DGLAP equation. And so the nice thing is that this is completely independent of the specific observables. And so you don't need to know anything about these energy correlators to get this result. So the renormalization group equations for the hard function come from Stefan's lecture. And so they say that this hard function evolve with some what is referred to as a splitting function. Shown here. And so if you trust this result from Stefan's lecture, you can then use that this overall expression has to be invariant under the particular value of mu, which you use to derive the similar analogous equation for this jet function. So if you use this invariance, I'll just drop some of the arguments for simplicity. You get that it also evolves in some particular combination with this splitting function. And so now what we can do is we can specialize to a conformal theory. And so we can just make an ansatz for the structure of this jet function. Yeah, I'll maybe have 5 more minutes, if that's okay. Yeah. Otherwise, I will not make it to the end. Yeah. So if you specialize to conformal field theory, you can make an ansatz for the structure of this function, namely that it has to be a particular power law with some exponent up here. And so what you can now do is you just plug this in to these equations, and you can derive a relation between the scaling exponent, which you'll observe here, and moments of this splitting function. And so in particular, what you will find is that 2 times this gamma jet is defined with an implicit relation to an anomalous dimension, which is called a time-like anomalous dimension, which is simply a moment of this splitting function. Like this. And so this is a slightly non-standard way of writing it. So it defines implicitly what the value of this gamma jet is in terms of this. And so unfortunately, I don't have time to go through how you get